Hi. Ever wondered how a roller coaster gets the crazy power to zoom down a track without an engine? Or how a bent bow shoots an arrow flying at high speed? It all comes down to one thing: mechanical energy. Today, we are breaking down everything you need to know about mechanical energy for your Class 10 board exams. If you want to ace your physics exams, hit that subscribe button, grab your notebooks, and let's dive right in. What exactly is mechanical energy? Simply put, it is the energy an object possesses because of its state of rest or its state of motion. It comes in two forms: potential energy, which is stored up energy, and kinetic energy, the energy of movement. Together, their sum makes up the total mechanical energy. Let's focus on potential energy. It is denoted by the symbol U. Let's look at the textbook definition. The energy possessed by a body by virtue of its changed position or configuration is called potential energy. But what does that actually mean in plain English? It means energy can be stored in two ways. First, by changing an object's height, like a heavy body placed high above the ground. Second, by changing an object's shape, like winding up a watch spring, compressing a metal coil, bending a wooden bow, or stretching a rubber band. None of these objects are moving yet, but they are holding a massive capacity to do work. In mechanics, potential energy is mainly of two kinds: gravitational potential energy and elastic potential energy. Let's look into gravitational potential energy. This is the energy possessed by a body due to its position with respect to a force of gravity. The gravitational potential energy of a body is zero when it is at infinity, because the force of attraction of Earth on the body is zero at infinity. As the object moves closer to Earth from infinity, its gravitational potential energy decreases. Because it drops below zero, its value at any finite distance from Earth is technically negative. Or, in another way, we can say that when you lift an object higher up from the Earth's surface, its potential energy increases because that negative value gets smaller. Now, let's switch to type number 2, elastic potential energy. The energy held by an object while it is deformed is its elastic potential energy. It is perfectly equal to the total amount of work you did to deform it in the first place. Let's look at the textbook definition. The potential energy possessed by a body in the deformed state due to change in its configuration or shape is called the elastic potential energy. This happens when an external force squishes, stretches, or twists an object, completely changing its configuration or shape. Objects have a stubborn property called elasticity. This is the built-in power that forces a body to snap back to its original shape the exact moment you let it go. Let's dive into a classic derivation, calculating gravitational potential energy at a height. To find this energy, we measure the exact work done in lifting an object from the ground up to that height against gravity. First, our baseline assumption. We consider the gravitational potential energy on the ground to be exactly zero. Imagine a body of mass m. To lift it up smoothly, without any acceleration, your upward force, F, must perfectly balance the downward force of gravity, which is mg. Now, let's apply the work formula. Work done, W, equals force times displacement. Here, our force is mg, and our displacement is the height h. Multiplying them together gives us W equals mgh. This work doesn't disappear. It gets stored directly inside the body as gravitational potential energy, U. Thus, U equals mgh. Now, pay close attention to how this energy changes during vertical motion. When you throw a body vertically upward, its height increases, so its potential energy increases. When it falls down, its height decreases, so its potential energy decreases until it hits zero at the surface. What if the object changes between two different heights above the ground? If a mass m is raised from height h1 up to height h2, the gain in potential energy is final potential energy minus initial potential energy, and this equals mgh2 minus mgh1. But if it falls down from a higher h1 to a lower h2, it loses energy. The loss in potential energy is initial potential energy minus final potential energy, and this equals mgh1 minus mgh2. Now it's time for a quick refresher. An apple weighing 0.2 kilograms detaches from a branch 10 meters high. On its way down, it gets stuck in a lower branch at 4 meters above the ground. What is its net loss in potential energy? Use G equals 10 meter per second squared. Pause the video for a minute and do the calculations, and drop your answer in the comments. Let's dive into kinetic energy, which we denote with the symbol K. By definition, the energy possessed by a body by virtue of its state of motion is called the kinetic energy. Think about it like this. A fast-moving stone can smash through a glass window pane. This is because its motion gives it the capacity to do work. A car in motion, the ticking hands of a clock, a blazing bullet, or a falling apple. If it has speed, it holds kinetic energy. But how do we calculate this mathematically? The textbook gives us a clever trick. The kinetic energy of a moving body is exactly equal to the work done by an opposing, retarding force to bring it to a complete stop. Let's derive the formula step by step. Imagine a body of mass m moving with a velocity v. We apply a constant opposing force F that creates a uniform deceleration A. The body slides for a distance s before coming to rest. From Newton's second law, our retarding force is F equals mass times retardation, or ma. That's our equation 1. Since kinetic energy equals the work done to stop it, we write K equals force times displacement, or F times s. That's our equation 2. Now we need to calculate that distance s. Let's use our third equation of motion. V squared equals u squared plus 2as. Here, our initial velocity u is v, our final velocity is 0 because it stops, and our acceleration is negative a because it's slowing down. This gives us 0 equals v squared minus 2as. Rearranging it isolates our displacement. S equals v squared over 2a. That's equation 3. Let's finish it up. Substitute our force F and displacement S back into equation 2. We get K equals ma times v squared over 2a. Notice how the deceleration A cancels out perfectly from the top and bottom. This leaves us with the legendary formula. K equals half mv squared. Now it's time for an exam-style brain check. Are you ready? If you double the velocity of a moving car while keeping its mass the same, what happens to its kinetic energy? Does it double or does it quadruple? Let me know your answer in the comments. Let's jump into another interesting derivation. Let's connect kinetic energy K and linear momentum P. Consider a body of mass m moving with velocity v. We know its kinetic energy is K equals half mv squared, and its momentum is P equals mv. Let's pull a quick algebra trick on our momentum formula. If we rearrange P equals mv to solve for velocity, we get v equals P over m. Now, let's take this value of V and substitute it directly into our kinetic energy equation. That gives us K equals 1/2 times m times p over m squared. Squaring the bracket yields p squared over m squared. Notice how the single mass m at the top cancels out 1m at the bottom. This is leaving us with K equals p squared over 2m. We can easily rewrite this to solve directly for momentum. Cross-multiply to get p squared equals 2mk. Then take the square root of both sides to get its twin form, p equals square root of 2mk. And there you have it. Now, let's see who can think like a real physicist. Look closely at the formula. K equals p squared over 2m. Here's the question. If a light object and a heavy object have the exact same momentum, which one has more kinetic energy? Let me know your answer in the comment section. Now let's move on to one of the most practical principles in mechanics, the Work-Energy Theorem. Think of it this way. When you apply a force on an object in the exact direction it's already moving, it speeds up. You did work on it, and its kinetic energy increased. That is the core of the theorem. The work done by a force on a moving body is equal to the increase in its kinetic energy. Now, let's prove it mathematically. Consider a body of mass m moving with an initial velocity u. A constant force F pushes it along its direction of motion, creating acceleration A. Its velocity changes from u to v over a displacement distance s. First, from Newton's second law, force is mass times acceleration, F equals ma. Second, mechanical work done is force times displacement, W equals F times s. Now we need to find our displacement distance, s. Let's bring in our classic third equation of motion. V squared equals u squared plus 2as. If we isolate s by subtracting u squared and dividing by 2a, we get s equals v squared minus u squared divided by 2a. Let's substitute our expressions for force and displacement right back into our work formula. This gives us W equals ma times v squared minus u squared divided by 2a. Watch the magic. The acceleration a cancels out perfectly from the top and bottom. Distributing the remaining terms gives us the relation W equals half mv squared minus half mu squared. Look closely at these two terms. We know that half mu u squared is the initial kinetic energy, Ki, and half mv squared is the final kinetic energy, Kf. So substituting those in reveals our final result. W equals Kf minus Ki, which equals the net increase in kinetic energy. Theorem fully proved. Now, time for another exam-ready mental challenge. A 2-kilogram object accelerates, changing its speed from 3 meters per second up to 5 meters per second. What is the net work done on the object? Pause the video and calculate Kf minus Ki and drop your answer in the comments. Did you know that kinetic energy isn't just about moving forward? It comes in exactly 3 forms, depending on the type of motion. Form number 1 is translational kinetic energy. This happens when an object moves along a straight line path. Think of a car traveling down a straight road, a freely falling body, or even a single atom of a monoatomic gas bouncing through space. Straight line equals translational energy. Form number 2 is rotational kinetic energy. This occurs when an object spins around a fixed axis. Classic examples include a spinning top, a rotating wheel, or planet Earth constantly spinning on its axis. Even diatomic molecules rotate around an axis while moving forward. Form number 3 is vibrational kinetic energy. This is a rapid to and fro motion around a central fixed position. Think of a wire clamped at both ends being struck in the middle, a flexible metal strip vibrating, or atoms vibrating inside a solid. Even a complex polyatomic molecule has vibrational energy mixed with translational and rotational forms. Here is an important textbook note. A body can possess either one or multiple forms of kinetic energy at the exact same time. For example, a rolling football or a moving bicycle wheel travels forward in a straight line while spinning simultaneously. That is a combined translational and rotational energy simultaneously. Now, let's look at the distinction between potential energy and kinetic energy. Point 1. Potential energy depends on an object's changed position or configuration. Kinetic energy depends entirely on its state of motion. Point 2. Potential energy is equal to the work done in bringing the body to that state. Kinetic energy is the work it can do before coming to rest. Point 3. Potential energy can transform only into kinetic energy. Kinetic energy can change into any other form, like heat, light, or sound. Point 4. Potential energy does not care about speed. Kinetic energy depends completely on the speed of the body. Now, let's explore exactly how energy changes forms in the real world. Potential energy changes into kinetic energy whenever it is put to use. For example, a raised stone holds gravitational potential energy. When it falls, that energy transforms into kinetic energy. Upon hitting a nail, the stone's kinetic energy does work on the nail, changing into the nail's kinetic energy and driving it deep into the wood. Let's look at another example, the archer's bow. When you pull back a bowstring, your work gets stored inside the deformed bow as elastic potential energy. The moment you let go, that potential energy instantly transforms into the kinetic energy of the arrow, sending it flying. Now, can you think about any more such examples? Just put them in the comments. Now, let's look at different forms of energy. Solar energy. This is the energy radiated out continuously by the sun. Because it is highly diffused and scattered, we cannot use it directly. Instead, we use devices like solar panels, solar furnaces, and solar cells to collect it. A solar panel uses a black-painted metal surface to efficiently absorb the sun's radiant energy and heat water running in contact with it. A solar furnace uses a large parabolic mirror to focus sun rays on a tiny area, creating temperatures high enough to boil water into steam, which spins an electric turbine. Meanwhile, solar cells use thin slices of semiconducting material to convert sunlight directly into electricity, though their efficiency is quite low. Heat energy. This is the thermal energy released when burning fossil fuels like coal, wood, or gas. In a steam engine, this heat cooks water into high-pressure steam, which is put to work to generate mechanical movement. Light energy. This is the form of energy that makes objects visible to us. While the sun is our natural primary source, objects like fire, candles, or burning lamps emit light energy right along with heat energy. Chemical energy. This is the potential energy stored inside the bonds of fossil fuels like coal, petroleum, and natural gas. When burned, it transforms into heat and light. It is also found in the food we eat. Plants convert solar energy into chemical energy during photosynthesis. Chemical reactions inside household batteries convert stored chemical energy into electrical energy when connected to a circuit. Hydroenergy. This is the kinetic energy held by fast-flowing or falling water. To capture it, we build tall dams across rivers to collect water at a high elevation. When this water rushes down through internal pipes, Its tremendous kinetic energy spins generator turbines to yield electricity. Electrical energy. This happens when two dry bodies rub together, causing free electrons to move from one body to another, giving them electrical potential energy. It also drives electric cells, where ions move between electrodes as a result of an internal chemical reaction. Nuclear energy, or atomic energy. This massive energy is released due to a loss in mass during nuclear fission or nuclear fusion. This mass loss transforms into raw energy, following Einstein's equation, E equals mc squared. We use it safely in reactors to generate electricity, or destructively in atomic weapons. Geothermal energy. This is the deep thermal energy released by radioactive nuclear disintegrations inside the Earth's interior. This heat cooks underground water reservoirs into hot springs, or high-pressure natural steam, which power companies can extract by drilling wells to run electric generators. Wind energy. This is the kinetic energy carried by fast-moving air masses. Historically, rural communities used windmills to physically pump underground water or grind grains. Today, we use massive wind turbine arrays to spin electric generators. Sound energy. Any vibrating object creates mechanical disturbances in the surrounding air layers. When these physical pressure waves strike our ear membranes and cause them to vibrate, our brain senses it as audible sound. Magnetic energy. This is the invisible field energy held by a magnet that allows it to attract magnetic materials like iron filings. We can create temporary, controllable versions using electricity, which we call electromagnets. Mechanical energy. As we covered in our previous lessons, this is the total kinetic and potential energy held by an object due to its height, its movement, or its altered shape. Now it is time for a quick challenge. When you use a solar-powered calculator, which two forms of energy from this list are interacting to make it work? You may drop your answer in the comments below. Now let's explore how energy is converted from one form to the other. Since we need energy in so many different ways, physics allows us to grab what's available and change it into exactly what we need. Number 1. Mechanical to electrical energy. Think of a hydroelectric dam. Water stored high up has potential energy. When it falls, that potential energy decreases, and its kinetic energy increases. This rushing water slams into a turbine near the bottom, transferring its kinetic energy into rotational kinetic energy to make the turbine spin. That turbine rotates the armature of a connected generator, turning that mechanical movement into electrical energy. So, an electric generator or dynamo converts mechanical energy straight into electrical energy. Number 2 is the exact opposite, electrical to mechanical energy. Inside an electric motor, when an electric current passes through a coil suspended in a magnetic field, a magnetic torque acts on that coil, forcing it to rotate. The shaft attached to the coil spins right along with it, converting electrical energy into mechanical movement. This is the superpower running your electric fans, washing machines, mixers, and industrial machinery. Number 3. Electrical to heat energy. In appliances like a heater, oven, geyser, or toaster, electrical energy changes into heat energy the moment a current forces its way through their high-resistance wire or filament. Number 4. Heat to electrical energy. This happens in a device called a thermocouple. When two junctions of two different metals are kept at completely different temperatures, one hot, one cold, a current automatically flows. It changes heat energy directly into electrical energy. Number 5. Electrical to sound energy. A loudspeaker receives electrical signals from a microphone and vibrates to change them into sound waves. Similarly, inside an electric bell, passing a current changes electrical energy straight into sound. Number 6. Sound to electrical energy. This is exactly how a microphone works. It captures the mechanical vibrations of your sound energy and converts them into varying electrical signals. Number 7 and 8 are two sides of the same coin. When you charge a battery, electrical energy flows in and changes into stored chemical energy. But when you draw current from that cell to power a device, that chemical energy transforms right back into electrical energy. Number 9. Chemical to light energy. When a candle burns, or when the oil soaked in a kerosene lamp wick burns, the stored chemical energy converts directly into light energy. Number 10 is a biology favorite, light to chemical energy. During photosynthesis, green plants absorb light energy from the sun and lock it away as chemical energy in food. Number 11. Electrical to light energy. When an electric current passes through a bulb, electrical energy changes into heat and light energies, making the bulb glow. Number 12. Light to electrical energy. In a photoelectric cell, or a standard solar cell, light energy hits the surface and gets converted instantly into electrical energy. Number 13. Heat to mechanical energy. In a classic steam engine, the chemical energy of coal first burns into heat energy. This heat turns water into high-pressure steam, which forces mechanical parts to move. Number 14. Chemical to heat energy. This happens when fuels like wood, coal, or biogas burn. It also happens when you light a matchstick or an explosion of crackers occurs, unlocking heat, light, and sound. Even inside your body, respiration converts chemical food energy into internal body heat. Number 15. Chemical to mechanical energy. Inside automobiles, the chemical energy of petrol or diesel burns inside the engine cylinders to generate mechanical movement, or kinetic energy, to spin the wheels. Number 16. Electrical to magnetic energy. This is how you build an electromagnet. When an electric current is passed through a wire coil wound around a soft iron bar, the bar gets magnetized, changing electrical energy into magnetic fields. Number 17. Mechanical to heat energy. When water falls from a height, its stored potential energy turns into kinetic energy. Upon striking the ground, a part of that kinetic energy turns into heat energy, causing the water's temperature to rise. You can also feel this when the moving parts of any machine get hot due to friction. Now, let's take a note of these two factors about energy conversion. 1. Whenever mechanical energy changes to other forms, it is always in the form of kinetic energy and not potential energy. This means stored potential energy must first convert into kinetic energy before it can change into any other form. 2. The dissipation of energy. When energy transforms, the entire energy never changes into the desired form. A part of it always changes into an undesirable, non-useful form, usually heat due to friction, or it is lost to the surroundings due to radiation. Because this part of energy is completely lost to us for productive work, we call it the degraded form of energy. With that, we have reached the end of the session. Before wrapping up, here is another interesting question. A roller coaster train of mass 800 kilograms starts from rest at the top of a hill at a vertical height of 60 meters above the ground. As it plunges down to the lowest loop at ground level, 20% of its initial gravitational potential energy is dissipated as heat and sound. calculate the maximum speed attained by the roller coaster train when it hits the lowest point at ground level. Please drop your answer in the comment section and don't forget to like, share, and subscribe the channel. See you again in another video. Bye!